Okay, hi everyone. Let me switch the scene. This. Okay, so can someone confirm in the chat that audio is working? It's my first time streaming with YouTube. Just want to make sure that everything is working as expected. Everything is working. Awesome. So I don't have an as nice view to the chat as I used to with Twitch. I don't have like proper setup yet. But hopefully that will be good enough. I also hope that there is not too much background noise. I am next to the street and the window is wide open because it's summer and it's very, very warm here. So, yeah. Let me see. Okay. So, very quick explanation of what I'm going to try to do today is basically get those chips. Let me take one out. So these are the MPW-2 prototype chips in QFN form that eFabless sent me very graciously. I have no idea what design it is. I'm just trying to bring up the Caravelle here, the management system, basically. And what I want to do is try to make them work with that board, which is the bringup board that Matthew Venn, that I designed with Matthew Venn some time ago to try to, make the MPW-1 chip do something. Now, unfortunately, they don't plug in directly for two reasons. The first one is that they removed the pins. Let me see if I have. Probably that camera is really. I'm not sure if I can actually focus. Yeah, I can actually focus slightly. So see here, there is no holes anymore. If we take an old breakout, so this is a WCSP breakout for MPW-1, and see there was castellation on the side, but there was also holes. And because at the time I didn't have the flexi pins and anything set up, the breakout board actually has been designed with pin header in mind. And the new breakout doesn't have the holes. It only has the castellations. And the other thing is that they actually changed the pinout. It's been flipped. So basically, if you take that chip, the pins, let me orient it the same way, like this. Okay, if those are the two, the pinout of this one is flipped like this, basically. They did that so that the breakout pattern on the QFN breakout is nicer, the routing pattern, which to me doesn't make any sense, but whatever. Because yeah, Eric, they actually don't do QFN. So the QFN are packaged separately by eFabless. So what they do is when they get the dies back, they take a few samples, they send them to be packaged in QFN for very early testing, while they do the bumping for the WLCSP. But 99% of the people will only get WLCSP. They just sent me QFN because so I could test some stuff early, but while the bulk of the chips are being bumped at the moment. So what I did to overcome that, because I didn't, let me try to refocus that. I have designed, I have adapted this board to work with flexi pins, and it's currently being manufactured by Aisler. But yeah, I didn't want to wait all the time because I'm only gonna get them like next week. I didn't bother swapping and changing the pinout because I figured instead of plugging in the chip like this, what I'm gonna do in the flexi pins is that I made a hole in the middle here, and I'm just gonna plug the chip backward, upside down, which flips the pinout, and so yeah, that avoided me redesigning most of the board. All I had to do is replace those female connectors by flexi pins so that I can just clip the board. But for today, because I mean, obviously, we're gonna try to bring up one of those chips. What I did is I made this. Let me see if I can focus. There was a picture of it in the thing, but it's basically one of those board here with the QFN soldered onto a blank breakout here, upside down like this. And then I manually connected every castellated pin with a small bit of wire so that when I plug it in, it should match the pins correctly. I hope I did that right, because if I didn't, this stream is going to be very, very short. I didn't test anything yet. I just wanted to do the initial bring up on stream, so you get to see, well, everything basically. So let me refocus that to the thing. Sorry for the quality of this cam. It's really crappy camera with a really crappy optics, but that's all I had quickly available. So this is designed to plug into an icebreaker, so I'm gonna actually plug it. And I need to find a micro USB cable because I didn't grab one in advance. Yeah, it's micro USB cable. No, that's a USB-C cable. Okay. This is micro USB. This is my trusty first icebreaker board that I got from SDN at Akadesh back on 2018, I think. Okay. So that's poured on. Yeah, sure. It's better than nothing. So I did make a quick drawing of the orientation of this board. I'm gonna double check it, but I think that this side is all the pins that have like the basically this side, and so that this goes like this. But before, I need to actually load the proper design on the icebreaker. So I'm gonna reuse exactly the same code that I have here. I already did check it out here, but I haven't actually built anything yet. So first I need OSS catsuit, this, I need a compiler. Okay. So icebreaker probably. Oh, okay, something I forgot to do. Get some modules in it. Good module. It's a module update. Okay. Fire, no icebreaker. Bring up. Okay. Let's see if that builds. that built it. It failed timing, but by almost nothing. And I also know that I'm not gonna be running it at 50 megahertz anyway, so it doesn't matter. Yeah, and programming it. Okay, nice. So because I haven't used this in months, I honestly don't remember how it works, and because I didn't document anything, yeah, I have to read the source code. So basically, at the moment, the only thing I'd like to do is get it to run some code. Now, some of the thing in here isn't gonna work directly because they changed. It used to be a Pico RV with like the Pico subsystem basically. In MPW-2, they already switched to the VEX using Lytix. Mathieu, can you confirm? I think that's the case, right? They had already switched to that for MPW-2, which means that the kind of access pattern that I was looking for on the chip select line are not going to be the same because it's not the same SPI controller. Yeah. But I just want to see some sign of life, basically. So I really just want to feed power and see what happens. So what I'm gonna do actually is I have a logic analyzer. I'm gonna wire it up to observe the SPI signals. So I'm gonna do that now. And then I might actually need to write a small test program here that just basically boots it at the nominal voltage because there should be no need to run it at like weird voltages to try to get it to run. It should run at the voltage that's been designed to run at. And I don't think I have a test like that already written. I'm just trying to find the appropriate test cables. Okay, never mind. I've already got it. So I need to connect all of this. So this is ground. I have ground here. And I'm gonna go with pin 1 being the reset signal. Trying to keep the view of the camera unobstructed, but I also need to see what I'm doing. Reset, I'm gonna do clock as the second one. So basically what the FPGA is doing is in this configuration, it will provide a reset pulse, a clock pulse, which is like instead of the crystal, it's a programmable clock. And it will also emulate a flash. I will be running it very slowly just because there is no point in trying to run things quickly here. So I'm gonna go with chip select. Clock. SPI clock, I mean. And then D0, D1 for the IO. D0 here and D1. Here. Perfect. And these are just used for now. I need the actual logic analyzer. Grab this that way. I would grab some painter's tape so that things don't move. Yeah, Conrad, they switched to Lytix, but as far as I know, that actually hasn't been without issues. I think one of the biggest one is they somehow screwed up the addressing of the wishbone bus. That's connected to the user zone, to the user peripheral zone. And that somehow limited the address space available to it. That has been correct. I don't think it's been caught in time for MPW-2 for it to be fixed. I think they fixed it in some later shuttle, but I couldn't tell you like which one it is. But I think MPW-2 will have that problem. As I mentioned, I have no idea which designs I have. There are some marking on the chips, and I've got different ones. But Matthew then tried to look for like a spreadsheet with like matching between projects and stuff like that, and couldn't find anything. So yeah, not entirely sure what chip I have, but at the moment it doesn't matter. I'm just trying to get the CPU up and running. And so the reason I don't actually have anything taped out myself on MPW-2. So that's definitely not my project. I have no idea what they are. The reason I got some of the chips, yeah, mystery chip. We need to figure out what they are. I mean, in theory, all the projects are open source, so it might be possible to identify them, right? Just by probing. What I was saying, the reason I've got some of the chips is because although they fixed the timing analysis and the clock distribution tree in the Caravelle itself, like the big block that contains the management processor. For MPW-2, there was still not top level timing analysis between blocks. And that means that there is actually still a hold violation in the IO configuration process. So yeah, does that sound familiar? And so no, we can expect the RISC-V to run properly, but the IO configuration process is going to have the same kind of issue as MPW-1 has, and that's why they sent some chip to me, is so I can actually try to run my my logic and the IO mapper system that I developed for MPW-1 to try to run it on MPW-2. They did test on their own because I actually got the chip like a couple of like a week or a week and a half ago, something like that. For some reason, FedEx took forever to deliver them to me, but whatever. And so in the meantime, they obviously made some tests in on their side, and they did manage to configure, using some software workaround, like I did, configure the IOs. I don't have much detail. I really just heard that from Mohammed, the eFabless CEO, like literally 20 minutes before the stream. So yeah. Okay, I need something to actually use the logic analyzer because I don't think I have anything installed on this machine. Let me actually. Sorry, I'm doing that in another console because I need root. Oh, never mind. Actually, I've already Pulse View installed, so okay, never mind. I have Pulse View. So let me start Pulse View then. Okay, yeah, nice. Let me actually name the signal so that I know what I'm talking about. This was reset. This was the clock that's provided by the FPGA to the thing. This is the chip select signal. That's SCK. And then this was D0 of the flash, which is going to be Mosey. And it's going to be Miso. And I also want to add a SPI decoder. The clock is going to be SCK, chip select, CSense, active low. Blah blah. Mosey, Miso. Okay, and I'm gonna stack this. Okay. I need to sample faster than that, 8 megahertz, and we're gonna capture like 10 million samples. Okay. So now we need to get this to run. So I'm gonna write a quick test. Let me read the chat first. Yeah, Benedek, I don't know which chip it is because I didn't tape out anything myself on MPW-2. These are just some chips that were sent to me so I can test the management system, which is common to all the designs. So I don't know what they are. So here we're really just trying to get the RISC-V and the I/O configuration running. We should be able to get the I/O under the control of the management core instead of under the control of the design. And yeah. So I have the simple runner test, which is sort of what I want almost. What the thread set reset auto? I honestly don't remember what set reset auto does. Oh, I think it pulses it every so often or something. Yeah. So yeah, we can actually just use the simple runner. Okay. I'm gonna keep that up. Actually, I'm gonna use another window. Okay. Okay. Okay, I need Pi serial or something. So I was just installing package in the other window. Okay. So VDD, all the chips are nominal 1.8. Oh yeah, wait. All the chips are nominal 1.8 volt, but I'm not setting the value here is just a raw a raw value and not a voltage directly. So let me the DAC is 1024 steps as far as I remember. Where do I do the yeah. Yeah, the DACs are 10 bits. So there's 1024 values, and the max value is 3.3, which means that if I want 1.8 volts, I need to divide that by yes. So I need 550. Yes. Simple whatever. And then here I can pass some more option. Let me. I think test VDD scan is a good firmware to run because the only thing it does, okay, it actually does something that I don't really want it to do. Test base. Okay, so I'm just gonna write a quick firmware that doesn't do it because this was to configure the IO on MPW-1, but I think the IO configuration process has changed in MPW-2, so this probably wouldn't work. So there's no point in me running this because it might actually write things at places it shouldn't and basically crash. So I'm just gonna have like an infinite loop that just does nothing basically. It does a bunch of knobs and then nothing. So I'm gonna try to run that. So I'm gonna use reset loop, meaning that it will reset every, I think like every 100 milliseconds or something, so that I can catch it on the logic analyzer. And then I want firmware source firmware test base. Okay, so that's not what I wanted to do. That's what I'm gonna try to run. A little explanation is that this is the port to talk to the the design that's running in the FPGA here. This configures the voltage level that I'm gonna be sending into the various rails. 558 is the equivalent of 1.8 volt basically. Simple runner is the name of the test that I'm running, and this particular test, sorry, will just load small RISC-V software and feed some clock and just continuously reset the embedded RISC-V. And this provides the software that it needs to, well, it will first build it and then it will load it. And it loads it into the SRAM inside the UP5K FPGA, and the UP5K FPGA emulates a flash, basically. It's faster than you know, having a real flash chip and having to flash it every time I want to try something. Let's see if that works. If that does, so I haven't plugged anything yet, but we should just see the thing executing and see the result on the logic analyzer, basically. This should have been configured. And so what if I do this? Yeah. So you can see that every so often I have a reset pulse, and then I have the clock that I'm sending to the chip, and then I have nothing on the SPI because I'm not doing anything. Right? So let me actually try to put MPW-1 chip to see what it does. So you can see that here we have some SPI activity. I shouldn't have captured 10 million sample because this takes forever to do the analysis, but yeah. And you can see that, yeah, it does a read and it reads some address. And this is completely bogus because the chip here doesn't execute correctly at that voltage, but that tells me that the flash is being somewhat properly emulated. Yeah, hopefully. Let me actually sample less. I'm gonna do 2 mega sample, and I'm gonna actually trigger on the falling edge of chip select, and I want 10% of trigger before, or 5%. 5%. Okay, so normally now if I do this, yeah, I should have a reset at the very beginning. No, did I miss the reset? Oh, is that the reason? What? Oh, what did I trigger? Oh, I triggered on this. Never mind. I wanted to trigger on falling edge of reset here. So did I trigger on falling edge of reset? Yeah, okay. Oh, the GPIO setup should be the same? Interesting. Because I was told that with the Vex, it was no like some kind of bit bang thing, which was completely different because there was not the state machine anymore and stuff like that. Oh, okay. Anyway, so let me unplug that chip. So I'm gonna double check the pinout of this because I want to make sure I haven't screwed it up. And that I'm not sending any bad voltages. So that's correct. This is like this. Okay, let me actually check that on the eFabless hardware thing. So yeah, just maybe I should have checked that before, but I want to because I'm suddenly having a doubt. Where's the hardware thingy? Is that this? Yeah, so breakout QFN. I hate the... Did I do that correctly? So these two... So what I'm assuming is that this side is the side that's connected to the various test signals. Can I see a schematic? Is there a schematic? PDF. So the style with all the control signal thingies is this one, J4. Yes. J4 is that. Okay, yeah. Okay, looks good. So here, if I trigger, there's nothing because I don't have a chip in. If I do this. So there's something. Oh, look at that. It does something. It doesn't do what I expect though, because actually maybe. I don't know. Because there is, I mean, there is obviously activity, so that I'm pretty sure I got the pinout right. And the chip is doing something right. But I would expect that activity to continue indefinitely because I wrote an infinite loop. Now, the Vex might have some cache, but I somehow doubt that they included cache in the Caravelle configuration simply because that needs SRAM. And I don't think they would have built that in. Anyway, we can have a quick look at what... it's possible that something else is going wrong and it's just crashing, right? But it's doing a read data at address 00 and fetches 64 bytes. Which sounds right. Let's compare what we fetch. Which is the data here, with what is actually in the flash. Does it? Okay, make test base.bin. It's a bunch of 13.0 and then 6F 01 FFE. So that doesn't look like it. Hey, Peter. Hi. I mean, some success in the sense that the chip isn't dead. It's doing something. It's not yet doing what I expect it to do, but I've barely started looking at it. So at the moment, I'm not sure what's going on. No, the decode might be wrong because the data that I see decoded here is 23, 12, 16, 26. Like that seems to vary every time. But if I look at Miso, it's like a very repeating pattern, like 1, 2, 3, 4, 5, 6, 7, like 8 times the same and then something different, which is like Okay, I'll do it. I don't remember how you tell xdump to not abbreviate. Dash v. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, and then something different. So I think the decode is some maybe misconfigured or something. It might have to do simply with the clock polarity, because yeah, you didn't find any cache. I mean, I am not surprised. I would have been very surprised if there was cache. So I'm sort of surprised that it's not doing anything more. Let me see if I can fix the decode. Yeah, I mean, I see why it doesn't decode it properly. Yeah, it's because I'm emulating the flash. Here, I'm outputting the data directly here on the rising edge. But the thing, it's like the logic analyzer doesn't see it, right? Because for it happened at the same time, but in reality, it happened like slightly after because I just reacted to the edge. I can probably tweak the decode, but I probably won't be able to decode both Miso and Mozi correctly. Yeah, here it decodes it. Yeah, no, it doesn't decode it correctly. Yeah, okay, never mind. But we can see that it's correct. It's because like this is sampled at 0. This will be sampled at 0. This will be sampled here. This will be sampled here. Because basically here it's sampled, and then immediately after the value change to the next one. So yeah, I mean, it's definitely returning the correct value as far as I can tell. Although, I guess maybe it's possible that that the flash controller of the flash controller of Lytix reacts differently, and it's actually sampling those values somehow differently, and that's why it's crashing. I mean, I don't know for sure it's crashing, but one thing that surprises me is that it fetches 64 bytes, which would typically be like a cache line fetch, like, you know. But if there's no cache, that doesn't make any sense. So I'm not sure what it's doing. I'm not sure. How can I know? I can try to execute something that's not. Okay, first let me actually check the voltage, because I didn't check that I'm sending 1.8 volt. I might have completely screwed up the. Let me see if I can put that in field. Let me find a ground. It should be ground. Then try VDD1, which is. Okay, these are on ground. This is ground. 1.827. So okay, I'm sending the correct voltage. And I'm sending the same voltage to all the digital rail. Let's see if I can find the other ones. I think this is one. Yeah, 1.8. Yeah, that's the. Okay. So I am sending 1.8 volt. So it should be executing. We can check if it's doing that consistently. Okay, if I retrigger. Yeah, it seems to be doing that consistently. Okay, so what I'd like to check is actually the timing of my output here. Like I'm pretty sure that's what's happening most of the time, is that there is the rising edge, and then just after I'm changing, just right after the rising edge. And that should be perfectly fine. So I'm assuming here the first one got decoded correctly, yes, and the two other didn't. Yeah. Okay. But maybe the Lightix controller doesn't see it, or maybe something else is wrong. Let me reread the program I'm attempting to. Okay. So I'm gonna go do this. I'm just gonna change the base software here and try to do something else. Like what happens if I suppress all the knob and do a tight loop? So the nice thing about this software is that I can just relaunch the command here, and it will recompile and re-upload and basically do everything it needs to do. And I should get the new software running here. And of course, just as I say that, so it only fetched 32 byte now. Interesting. Okay, so what's happening here, by the way, is this is the first jump. If we look at actually, let me do this here, maybe. Make test base dot bin test base. Okay. 6F, which means we should find 2 bits at one and then 4 bits at once. And so we have 2 bits at one and then 4 bits at one. So yeah, here you have the jump backward, and then you have a bunch of knobs, and the bunch of knobs are just from the previous firmware, basically. I think it is, Matthew. I think it is. It's just that it seems to have some cache. I don't know. Because let's say I redo. So this previously was fetching 64 bytes because you had 8 knobs. 1, 2, 3, 4, 5, 6, 7, 8 knobs. Each takes 4 bytes. That's 32 bytes. And so it was fetching already the next block of 32 bytes. Now let's see if I here I'm suspecting that it's only gonna fetch against 32 byte basically. Because it's gonna fetch 7 knob and then the jump, and it won't fetch the next one. I somehow wish that Pulse View didn't reset. And I'm wrong. It fetched the next one. Okay. Maybe there is a prefetch. Maybe let's try to find the source of this vex core. if you happen to have a link, Matthew, that would be insanely helpful. Yeah, Peter, sorry, I didn't see no command. Yeah, but it's better than the last one, but there are still, unfortunately, a couple of issues with it, which is why I have some of them. So this would be it. I'm assuming that they have tags with MPW-2, right? MPW-2B. Yes. Do we have the Vex? Okay, great. There is 4 of them. Which one did they use? Because there is one which min debug cache. Oh, great. There is also PyCoRV, so that definitely looks generated by Lytix. So I need to do is find the Vex core in this. You posted the link? I don't see the link. Oh, but maybe there is something like that people can't post link or something. It's honestly the first time I'm using Am I sure that the code is being linked to the same address that the Vex? Well, 100% sure. No, but the jump is a relative jump, so it shouldn't matter. Yeah. Yeah, sure, no problem. I just don't see it, but I'm pretty sure I found what is this? I mean, the Caravel Management SOC Lytix tag MPW-2B. I just need to find which, because the 3 variants are included in here. And yeah, what is this? No. Yeah, of course, if I search Vex, I'm gonna find like 6,000 things. Vex. Okay, here. Oh yeah, they're all named Vex Risk 5. It's just which file was used for synthesis. How do I know that? Would that be in the make file? Okay, so they did actually use the one with cache, mean debug cache. So that's why we don't see more access when yeah, it's because yeah, the things is cached basically. So it's actually behaving as I would expect, knowing that there is cache. And the fact that we see the next cache line in is probably just prefetch, because it's probably prefetching the the jump basically is pipeline flush, and so it probably fetches the next instruction but doesn't actually use it for anything. Okay. So if the vex is executing correctly, I'd like to know how much cache it has though, but I'm not sure how to know that, because they only included the I mean, yeah, I don't. RTL, Verilog, RTL. So that's the one that's used. That's the one that's being used. The primes, I don't know how this was generated. I don't know if that's the base configuration from Lytix, because Lytix has a something like that, right? If I go to Lytix, that's yeah, interesting. No, it's Lytix up. Lytix up, I think, is where I want the thing. I think this is where I'm gonna find the Python data CPU vectors 5. Yeah, this. Because here there is a vex min. No, there isn't. There is no vex describe min debug cache. So that means that's something they generated themselves. Would have been nice to have the source for that. That's somewhere in here. CPU is vex risk 5. CPU variant is minimal plus debug. There's nothing about cache. Nothing about cache here. And they didn't put anything related to spinal HDL as far as I can tell. Yeah. So I have no idea which configuration this was generated, which means to know which kind of cache we have. The only thing I can do is to read the Verilog source that have been generated from. So who did that? Jeff D. It would have been nice to know where this comes from. Okay. Let's try to figure that out. Maybe there's like a... I mean, there has to be a memory array declared somewhere here, right? That's the register file. Oh, actually, we can look for RAM style. So that's the cache. We have an instruction cache, which is... am I reading that right? That it's for 128 bytes, 16 words of 4 bytes, 16, 16 by 4. No, 64 bytes. And then we have 2 ways. I'm not gonna lie, I'm a tiny bit confused by this. Okay, so we only have instruction cache and it seems very small, which on the other hand makes sense that it's very small because it wouldn't be using SRAM blocks for the SKY130. It would be using basically SRAM memory implemented in flip-flop, which would be basically huge, if they had put like a 1K or something like that. But that means that it should be fairly easy to actually trash the cache, right? Like if we put 16 thing here like this, we should actually trash it. And so we should see the fetch basically restart all the time here. And that's exactly what we see. Now we see fetch all the time because we have a loop which is larger than the cache size, so we're constantly trashing it, and so we see like fetches of cache lines every 32 bytes every time. So okay, so the CPU seems to behave as one would expect. Nice. So I guess the next thing would be to try to configure the IOs, because that's the thing that's supposed to be problematic. I don't have all the IOs wired here, but what I'm gonna do is I'm gonna take 2 of the pins here, connect them to... I don't have IO0 connected, I have IO 11 and 12. So I'm gonna connect those. IO 11 and 12. And so what I would try to do is basically configure them as digital output under the control of the management core and just toggle them from the software. For that, I need to be able to know how the IO configuration system works in this. And unfortunately, I don't know if there is documentation somewhere about that. Because I was told that this thing completely changed, so... I mean, something else we can actually find completely unrelated, but we can actually try to run it at a different voltage, because it's supposed to run as low as 1.2 volt, right? So if we do... Let me actually try that, I'm curious. If I run it at 1.2 volt, it would be 3.72. Curious if it still executes correctly. I I mean, I'm running it relatively slow, right? So yeah, seems to run just fine. It does the fetches exactly as one would expect. Nice. I'm gonna check that it's actually changed the voltage. Yeah, well, when reading your first message and looking oof, I was kind of wondering what the hell is oof. But yeah, it looks good. It's nice that it runs under that the RISC-V seems to run nicely under high large voltage range, because that means we could actually potentially, you know, play with the voltage during the IO configuration process as well, to try to get it to work better. Maybe there's a combination that actually works better. You know, as you've shown with changing the voltage, the setup and hold requirement varies, and so maybe we can actually get it to a point that works, and then we once the IO are configured, we can switch to the nominal voltage and let me check. I'm actually outputting 1.223 volt. Okay, let me restore it to 1.8. Okay, IO configuration. I need to find how that works. If anybody else has anything they want me to test before going to IO configuration, or if they have anything they want to ask, feel free to ask. I lost my chat. Okay, here. Never mind. Okay. Time is it? No, oh, okay, that wasn't too slow. So there's the docs. LA junk. What the hell is that? Flash file control. Control was no. Okay, as usual, I'm just gonna read the source. Yeah, actually, that's a pretty good idea, Matthew. Is there some in here? In the maybe in the digital validation that they have some example. Wait, where did they put DV? LVS Lytix. Okay, so the switching to C pretty quickly. Yeah, that's all the stuff from Lytix. I'm not really interested in that. Okay. It's a bit weird that there is PyCore V32 specific stuff in there, because that's setting up the special IRQ thing from the PyCore V, but it's using a Vex. I'm looking at the wrong thing. Oh yeah, looking at the wrong thing. Yeah, there's nothing in there. Start Pico, I'm assuming start Pico V. I mean, if there is assembly, that's fine by me. Good car print, never mind. No. I mean, is there like a main somewhere? Start simple system command. Put X. No. Sorry, I have no idea what I'm doing because I've never looked at that before. And I don't see. Like I'm looking for like a main.c or something. There's nothing here. Okay, maybe this. Okay, so there is one GPIO pin like this. One GPIO pin that's 0 and 1 basically. So we could actually test that first instead of using the that doesn't use the IO configuration, but that can confirm that our firmware runs. So I'm just gonna reassign the purple here. I'm gonna connect it to the GPIO pin, which is, where is it hiding? Wait, where is it? Oh, here. Okay. And so what I need is basically do this. I'm just gonna reuse the same firmware. Like I don't. So I need to find where those GPIO are defined. Maybe firmware. There's somewhere here, right? I can get it in the docs. Docs. Generated GPIO. That's the. So that's the base. Okay, so let me oh, that's interesting. GPIO mode 1 is 0 and GPIO mode 0 is 4. Okay. Yeah, I know. I'm missing the syntax. I'm just putting the offset here. Okay. And so the X, yeah, but the X, what I'm gonna do is the X, like I need the source code. For it so that I understand, or yeah, maybe the binary so I can decompile it, maybe. I mean, I can decompile the X as well, I guess, but yeah. And you can send them to me by email if you want. I'm just gonna put 0. Well, actually, I'll just put 1 here in T0, and then I can just do show word T0. No, yeah, T0 into GPIO mode 1 A0, and in mode 0. Yeah, that's weird because isn't EAN would be interrupt enable? Why would I want that? Oh no, EAN is tri-state control. What? Who names IEN tri-state? What? Am I the only one to think that EAN is interrupt enable and not tri-state control? Because that looks like tri-state control. Send to Discord. Oh, thank you. I'll have a look when I'm done with the GPIO here. Okay, I'm actually not gonna do that one for the time being. Because I don't have any interrupt handler setup, so I definitely don't want to trigger an interrupt. And then I can do this to GPIO out A0, and then I can do 0 to GPIO out A0. So that should toggle it, and then I can do G1B, and then 1. Okay, and here I have my infinite loop that toggles the GPIO. Right? And that builds and that creates that software, and so I can try to run that. And now if I take the logic analyzer and I do run, look at that. Oh, GPIO is toggling. It's D7, it's the purple wire. Okay, so the GPIO works. That's nice. At least we have one way of communicating information to the outside should we need to. So that's pretty cool. Actually, I'm guessing we have a UART too, right? Do we? Do we have a UART? No, we don't. I'm dreaming. We don't have a debug UART on this. Shows the logic analyzer. This is the logic analyzer. So you can obviously see when we basically enable it or something, that's probably switching the mode, and then at some point it restarts executing, right? And we can actually see that it's lower, it's longer in the low state, probably because there is the overhead of the jump, right? Because we set it to 1, then set it to 0, and then we have the jump, and the jump probably takes 2 instructions because of the pipeline flush. So the down phase is actually longer than the up phase. If we want it to be 50%, we'd probably need to do something like this. Then we'd probably have a 50% square wave. No, we don't. What? Okay. I'm guessing the overhead of the jump might be higher. Than 1? Might be. Might be 2 cycles. Still not. I'm starting to wonder if it's actually executing my code or not. Because, I mean, you can clearly see that here we have 1 opcode, and then because you can look at X clock, right? X clock is the clock we provide to the... Yeah, I don't think so, because this is the clock that I provide to the CPU. And so you can see that this basically has a duration of 1, and this has a duration of 2. Like, they're not perfectly aligned because of the delay, but like this is 1. Can I measure things? One, two. So that's sort of a period of 3. Let me try to sample faster. Okay. My sampling of X clock was definitely bad because I obviously my clock is faster. That's why I didn't have a good correlation at all between the thing here. So this seems to last for 1, 2, 3 clock cycles. And this lasts for 1, 2. I'm probably missing 1 here. I can try 24. That usually doesn't work very well, but yeah, that didn't work. Oh, and okay. No, not what I wanted to do. How do I save this? The thing is, Pursue, once it crashes because of sampling, there's nothing you can do, and I'm kind of hoping that it saved my setup. Let's see, it's not quitting, which means I'm gonna have to kill it. Ah, that is just so annoying. For like, okay, it saved that. Thank God. I wanted to trigger off floating edge. It's at 5%. Okay. Now at 24 megahertz, it's not stable. It's crashing, and no, it's not gonna do anything. And if I try to retry, oh, never mind. It actually worked. Yeah. So I can retry. With more resolution. But what I can do is actually just diminish the clock. Okay, so not center, but what I'm gonna do is change it to divide by 16. So I'm basically halving the clock that I'm sending to the chip, so I can sample it easier. So now if I sample at 16 megahertz, which is gonna be more stable, I'm gonna have a better. Yeah, because now I can see like the X clock is much better and everything. But yeah, it's actually taking. Do those knobs actually do anything? Okay, so this is high for 1 microsecond. No, those knobs don't seem to do anything. I'm a little bit confused. I'm a little bit confused by that. Why isn't that changing anything? Like, if I command that out, that's gonna not toggle anymore, right? Yes, it's not toggling, which is what I expect. So it is updating the code that I'm writing. Okay, yeah. Okay, no, I added so much because now it does a flash access between every fetch. It's actually like not executing in cache anymore, which means it does a SPI fetch, which means that the loop takes basically forever. Okay, so now it's longer. Okay, so what I'm assuming is happening is that when I put 1 or 2 knobs, it doesn't actually do anything because the SW is it's an external bus access, and so it probably takes more than 1 cycle. And when I do the knob right after, because it doesn't need the bus interface, it can actually probably execute while the SW is actually still being executed. So that's what's going on. And that's why adding 1 knob isn't changing anything, and you need a couple of them to do anything. Can probably remove one here, and that should be about the right amount. Yeah, that looks more or less square. Yeah, I mean, up to the sampling error of the. Yeah, That looks fine. Yeah, it's with the when you execute stuff with the PyCoreV, it's much easier to figure out like mentally what's going on because it's so simple. But the Vex is already much more advanced for a RISC-V CPU than the PyCoreV, and so sometimes it does things, and you need to really think about what's going on to predict it. I mean, the I/O I'm trying is the dedicated GPIO pin. It's not one of the user I/O. So that's the only such I/O there is. So I can't try anything else because I don't think there is any other thing I can control like that with direct access. So now I need to look at what you sent for the GPIO configuration. So let me download that. I need to transfer that to another. I'm downloading on my laptop because that's where I have Discord open. I need to transfer that to my other machine. So give me a second here. Okay. So let's see, what did Matthew send us? Okay. Okay, so that actually looks exactly like the previous one. Interesting. Yeah. I mean, that's exactly how it used to work. I mean, yeah. So I'm assuming you've run that into the digital simulation, right? So I'm guessing it works. So I'd be interested to know what how this thing works. Hmm. I mean, what they did in the Verilog, because they mentioned they changed it, so that's sort of why I'm curious as to how does the other how does the old method still works if they changed it, or did I misunderstand what Tim Edwards was saying? Let me look at the Verilog. Okay, well, that might actually just be the management core. SRAM only access module IO. Oh, there is actually a serial transmit and receive. So there is a UART somewhere on this thing. Yeah, I think some of the first IOs are dedicated for this, if I remember correctly. So that's the exported wishbone bus, GPIO. Okay, so the I just as the ENE pad is the input disable. Okay, so that makes sense now. It's not interrupt enable, it's like input enable, as in the input path of the GPIO, like macro. Okay, I'm just noticing I'm completely not centered in my webcam, but so yeah, what I'm looking for is all the user IOs, and the user IOs are not here. Not here. What the fuck are they? GPIO, logic analyzer. MPG, that's the wishbone bus. There's nothing there. Okay, Matt, I think posting URL doesn't work because I can't see what you're posting. Let me actually try to... Okay, I think I've just made you moderator on the chat. So can you try to repost the link? Because at least I'm not seeing the link, so I'm assuming nobody does. I mean, I'm assuming that you posted a link. Yeah, okay. No, I see the link. So apparently, yeah, things are not visible. Okay. So let me try to open that here because of course I don't have the chat. Actually, can I open the chat here? Can I find my what? Yeah, okay. Can I find the chat in here? I'm sorry. I didn't realize that in the YouTube chat. I have no idea how and you see I would have assumed that it would tell you that if you post a link that doesn't. Okay. Read only. GPIO configuration and routing MPG. So it's like in the housekeeping block. Is that what you're saying? Okay, I need to reopen the chat here. Yeah, but do you know if that's already in the MPW-2? Because I don't want to really be looking at documentation for like this chip. I need the yeah. Version. There's only latest. I can't. I mean, I don't really see how that works because I mean, okay. So that's the management core wrapper. Okay, so all the GPIO stuff is. Okay, so oh wait, what? No, that doesn't explain how Because the way I see it here, the only way to configure them would be to go to the housekeeping SPI, which is like SPI slave that's on a SPI master internal bus, which is also accessible externally, right? That used to exist in the previous thing too. But then how does your code works? Because this just writes a few memory mapped register, right? And so that's my question is, where is that in there? Because the way I look at this schematic, doesn't exist. New includes in the C file. I mean, honestly, I'm not sure how they would have, whatever define they would have made, they couldn't make like C go with like equal something. Like that's just not happening. Yeah, I mean, this is still a memory mapped address and exactly the same one as it used to be. So somehow, somewhere, there is still a memory map thing that controls the GPIO. And that's what I'm looking for here. It's like, where is that? Wishbone bus to GPIO. So you mean it's going through that bus? Or through this? Oh, HK, housekeeping. Oh, no, because that's only in that. There is no output, no address here. It's just data. What the hell? No, never seen that in Verilog before. I mean, anyway, let me actually check that the address have not changed. I did just search for them, right? No, this 26044. So IOConf was indeed at 2.6. And 0x20 plus 4 times 8. Okay, so it did change. The defines slightly changed because previously it would have been at 20. So something changed in this. So I need to check this. So xfer is at 0. Yeah, so now it starts at 24. And it ends at yeah, after B8, BC. And then the trigger load is still at offset 0. It is still at offset 0. So this should work. So my idea here at the moment is that if the old IO configuration process still works, and it looks like it does because Matt ran his code in digital validation using the simulation models and stuff, and it still works. So somehow this method of loading the registers should still be supported. That means I actually should be able to run the old IO mapper thing as is, basically. The only thing I need is the test honest. Let me get that. Okay, so this is the test honest for the IO mapper thing, which, as far as I remember, goes this, and then this needs to be wired to some IOs here, but I don't remember which ones. Let me recheck the Verilog sources. Four and five. Probably goes like this. And then the one is the gray here. So I'm gonna try to run the IO mapper. IO mapper. So IO min that I'm gonna map is IO 11 because that's the first one where I actually have a. I didn't populate all the headers because I didn't need them all. So I'm gonna start at 11 and I'm gonna stop at 11 plus 8 because I only have 8 things. So that's 18. Okay, so it tells me to connect the sense wires. So I've connected one. No, actually, I haven't connected one. Two. Three. 4. 5. 6. 7. and 8. Okay, let's try to run that. I'm actually curious if it's gonna do anything. To be honest. So it doesn't look like it's doing anything. So that's the software I used for the MPW-1 debug. And what it's doing is it's basically trying to shift, not random value, but like different values or different combination of values into the IO configuration registers to find one value that actually changes the IO state from floating to not floating. And it detects the floating value because using some pull up and pull down resistors, it basically tries to pull it up, pull it down, and if the value you read is follows whichever direction you pull weakly, then it's not driven. And if it doesn't, that means that the IO buffer has been enabled and it's actively being driven. Sorry, someone is keeping sorry, I'm just gonna quickly answer because it's the efabless CEO, but like I'm in the middle of a stream. I can't really talk right now. Okay, so sorry for the interruption, but so it didn't find anything. So apparently that's not working. Why? Trigger a load. So I want to. If it does that. Okay, yeah. So what I want to test is if the loads finishes at all. Um, and the way I'm gonna do that is, how will I do that? I mean, the easiest would be to use the GPIO that I have and that I know works. So if I go back to my test here, which just toggles an IO, right? Okay. remove that out of the way. So what I'm doing here is I clear all the configuration registers. Actually, yeah, I should have done that like this. This cleans all the IO conf register between this address and this address, and then I'm gonna trigger a load. And wait for it to complete. And then when that's done, I will start toggling the IO, which means that if the load never completes, that means that I never get to triggering the IO. So let's do that. And we can see that we do get to trigger the IO. Yeah, toggle the IO. Yeah. Chip F1 is yours. Okay, so do I have some of these? Yeah, so I have F1. That's an F1. Unfortunately, I have no idea which one is the one that's mounted here because, I mean, it's currently stuck against another PCB, and so I can't tell you what it is. Let's see what the other ones. So I have. Okay, so of course in the chips that I have left, I have two F1 left and two B7 left. And I know that the one that I had here was also the same. It was either F1 or a B1 or a B7. But of course, I don't know which one. There's like no way for me to know. So I will only be able to test. And it's so, okay. If it was your chip, what peripheral is there? Is there any wishbone register I can read or write, or that should have some value or something like that? What's on there? Yeah, I should have maybe looked at which chip I soldered before I soldered it, but the board with the flexi clip is coming next week, so I'll be able to test then. Designs are enabled. Oh, yeah, true. So I want to try to configure IO. I don't remember which one is easiest to configure. It's IO1 or the latest one or the last one. Okay, but anyway, that doesn't really explain to me why it isn't working. Actually, I'm gonna configure the GPIO first. I'm gonna use A1 so that I can keep it initialized. A1, A1, A1. Okay. I don't need those knobs. What I want to check is how long the load process actually lasts. So I'm gonna set it to 1 and then set it to 0. I'm gonna set it to 0 here. So I'm configuring the GPIO and setting it to output 0. And then just before I trigger the load, I set it to 1. And then when it's done, I set it to 0 again, just to see how long this lasts, basically, the loading process, to make sure it's not like immediate and return and doing nothing, basically. Okay, so interesting is it's not toggling. Did I screw up something here? Am I using T0 for something else here? No. What's going on? So D7 here is the GPIO, right? A1. Oh, never mind. I'm using A1 and A2 here and I'm overriding them. So obviously that's not gonna work. T0, T1, T0, 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 T1. Any see if that works better. Okay, so now I have my toggling, and so yeah, we can see that here, this is where the loading process begins, and this is where it ends. And if we have a quick look at how long that takes. So this says 3.2 megahertz. I don't actually trust that. One, two, three. Wait, 1, 2, 3, 4. Okay, so the clock that I'm sending is about 3.2 megahertz. And the loading process seems to last for 160 microseconds. So 160 microseconds multiplied by 3.2 megahertz. That's 512 clock cycles. Which I guess is plausible because each IO configuration register is like 13 bits, if I remember correctly, and there is 37 or 39 of them. So it takes about 507 clock cycles to ship them out. So we're, so what I did, okay, if you didn't follow, I just timed. So I configured the external GPIO so that it starts outputting a 1 when the IO configuration shift starts and output 0 when it's done. And I measured how long it is, and it's about 512 clock cycles. I mean, it's a very rough measurement, but it gives you an idea. And I know that that there is 39. No, there is actually 38. Sorry, 38 IOs on the chips, and each of them is 13 bits. So it would take 494 cycles to shift it entirely, and so that gives, which is very close to the 512 that I just quickly measured, right? So that tells me that okay, this is actually doing something that is plausible. Obviously, there still might be something wrong in it, but it's not doing nothing, please. So I can try to just configure an IO like it's supposed to work. So let's try to configure IO 11, and I'm gonna try to configure it to be driven by the management core. So for that, I need to so I'm just writing some comments so that I remember what it does, but okay. I want to try to configure IO 11. IOconf 14. I say I want to configure IO 11 and I put 14, but yeah, okay, never mind. IOconf off 14 and the offset is 0. Okay, now the question is, what do I need to put in that register to configure what I want? And for that, we need to refer to the documentation that was okay. Actually, this is what I'm looking for. Management enable. Yes, I want that to be enabled because I want it under the control of the management core. OABN, output enable inverted. So I want it to be enabled. So I want it to be 0. All the rest, as far as I remember, can be 0, except for the digital mode where I want it to be an output, and so that's 110. 110. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And 110 is gonna be 1, 8. So this should configure IO 11 to be under the control of the management core. I made a mistake. Yes, software 0. Oh, sorry, it already includes A0. Okay. So I don't expect necessarily this to do anything because even though it's under the control of the management core, I'm not telling it to drive high or low, so it might not actually do anything. What is this? Oh, is it because it's undriven or something? Wait, but something doesn't. Did I screw up the rest of the code somewhere? Okay, because here I see the IO is 0, and then I can see my need peak where it's waiting. Okay, and when I do this, things go complete. When I do this, things look like crap now. Like I don't have my nice peak. I have some weird shit here, and then what? How is this changing anything? Why is it changing anything? Sorry, I'm looking. I should have something to drink, and I can't find what I did with it. Okay, it's here. IOConf offs 11. IOConf offs 11 is 0x24 plus 4 multiplied by x a0. Okay, so that sounds perfectly reasonable. SW is forward. What the? Yeah. So I have the Let me actually disconnect. I mean, I don't need to disconnect the harness, but I can disconnect it because I'm not using it at the moment at all. Just to make things more clear about to what is connected to what. But I have the purple wire of the logic analyzer, which is track 7. That's connected to the GPIO that's dedicated to the management core. That's not a user. That's not one of the user IO at all, right? It's one of the pin around here. And then I have the blue wire here, which is connected to IO 11, which is the IO I'm trying to configure. So I mean, D6 maybe should toggle. I'm not sure because at the moment it's high. It might be just a pull up inside the Salelae of honestly, or it could be that it's just pulled up internally or just randomly at high. And I'm trying to enable it as an output, which might drive it high or low because I'm not currently initializing to which value I want to drive it. But what is worrying me at the moment is that just adding those two lines here is changing the behavior I'm seeing on D7. And that shouldn't happen because that's the... I mean, obviously it still gets to the point where it it's toggling things, but still, that is weird. Oh, maybe it's just a matter of. Oh yeah, well, I think I understand what's going on. Okay, yeah. Here, when it goes low, you know, here I set it low and then I start toggling it. And then here I can see it go low and then it starts toggling way after. But that's just because this, it just so happened that this was aligned with a 32-byte boundary, and so it was fetching. It took time for it to go and fetch the next instruction to start toggling. And then when I added those two instruction, what's going on is that it goes low here, and then at that point it needs to start fetching a lot of data to start executing. That's why it stay low for so long. And then here it goes high, waits for the load process to finish, and here the load process finishes, and it immediately start toggling because it actually already fetched the cache line that had the code for the toggle inside. Okay, so never mind. That was kind of a false alert with okay me figuring out it's less convenient. The cache makes it much less obvious what code the CPU is executing. On MPW-1, because there is no cache, whatever address was fetched from flash was what the exact instruction that the PyCoRV was executing, basically. Meaning it was much easier to follow, basically. So yeah, I mean, at least it doesn't look like it. I can check if it's. How can I check that? I mean, yeah, I can try to output something to it. Um, so this is the data. C and 10 is the registers where the output data is. C and 10. And so what I can try to do is actually LE T0 and T1. So I'm basically toggling all the controlled. Okay, but you can see that it's not toggling, which means the IO was definitely not configured as it should have been. Because if it was, D6 would be toggling, and it's not. So, I can try probing other IO to see if one of them got enabled, but it's unlikely. But Let me actually do that with the multimeter because it's gonna be much faster than me trying to trigger every time. Can you can't see that. Okay, so you can see that more or less. Because the IO is toggling all the time, what we should see is like a half voltage, but more or less stable. That's just floating. Yeah, just floating. Yeah, here all the IO seems to be floating basically. So yeah, that didn't enable anything. That definitely did not do what it's supposed to do, which is turn this pin into an output. So what I like to get working is the IO mapper. I'm not entirely sure why it's not. To be honest, because let me think. Why wouldn't it work as is? I mean, obviously I had to change a couple of things in the file, but I did change them in test IO mapper. .24 and BC that I changed. The base address is the same. IO conf offs has changed, but it's the same, and the rest works. So that should have worked. Why wouldn't it? If anybody has any idea, feel free. But at the moment, the only thing I can say is that indeed there is a problem again with the IO configuration in MPW-2. So I still want to find exactly if there is another. No, Caravelle. So that's the management sock, but that doesn't seem to contain the Caravelle itself. So I'm guessing in Caravelle I'm gonna find the rest. Okay, I definitely want the tag MPW-2. Okay, so that's what Matt was saying. Okay, that they shifted this, and there is a wishbone interface to the management sock. Wishbone backdoor. Okay. One D. Okay, GPIO address and oh wow, that is not in order at all. 24, 25, 29, 28. What? Okay. I think I need to study this in a little more detail. To figure out what exactly is going on and how I can try to drive this. If anyone has any questions or anything they want me to try before I end the stream, go ahead and ask. What for sure is that the Vex, since indeed seems to be executing and seems to be executing way more reliably than it was in the previous versions. The IO configuration isn't working out of the box as far as I can tell. The IO map process that I developed for the last MPW doesn't seem to be working out of the box. I have to think about why that would be. I don't have any immediate idea right now, so that's why I need just to think about it. See if I can think of anything, and reading the how the new GPIO configuration block works might help figure that out. So no questions? Well then, I guess that will be all for today. I don't know if I'm gonna. It depends. What I can think of. If I will stream a next debug session, or if I will just do it or not, because I might just think of something and just try it quickly, and it might work or not. I don't know. But thanks everyone for joining. If I can actually get something running, and it turns out that the chips are indeed matte chips, I'm sure. I mean, I'll talk with him. Maybe he wants to be the first one to actually get them to run. So I might leave that to him, or maybe we can test them more deeply because we know what's on those. I don't know. We'll figure that out. Yeah. Thank you for joining, and yeah. Subscribe to the channel. I think I will probably try to stay with YouTube, just not to, I don't know. I don't really see much advantage to Twitch, and it's more convenient for me to directly have the VOD on YouTube, I think. I need to figure out the chat, if I can enable anyone to post links, because it's kind of annoying that I have to make people moderator to allow links. Not a good thing. But yeah, unless you have, any preference or anything, feel free to leave them in the comment or anything. For the record, if you want to ask any question or talk with me, you can find me on the 1-Bit Squared Discord. Is most likely the channel where I would be the easiest to reach, and the easiest to reach. Sorry. I'll leave the link in the description and everything. Thank you, and see you in the next one.